Hi everybody, today is our note on the characteristics of polynomial functions. You need to have already completed the work on your own, the handout Exploring Polynomial Functions, before you watch this video. So make sure you do that with your textbook, and this should just be a summary of what you learned there. So today we're going to define the terms turning point, leading coefficient, and absolute maximum or minimum, as well as describe key features of the graphs of any polynomial function. So their end behavior, the number of turning points, the number of zeros, and the symmetry, just by being given an equation or a graph. So first we have some definitions. First we have the definition of a turning point. So a turning point, let me just get a pen here, on a curve is where the function changes from increasing to decreasing, or vice versa. So this looks like, if you just put oh boy, I gotta get used to writing on this pad again. If you have a function that looks like this, you'll notice that we have two turning points, okay? So this is a turning point, A, and B is a turning point as well. So A is a turning point because the curve is increasing and then changes to decreasing. B is a turning point because the curve changes from decreasing to increasing. Okay, a leading coefficient is, let me just scroll down here a bit. Okay, so a coefficient, remember, is just the number in front of a variable. So a leading coefficient is the coefficient of the term with the highest degree in a polynomial. So if it's written the correct way, it would be like the first coefficient. So for example, if you have y equals 4x cubed minus 2x squared plus 3, something like that, then the leading coefficient would be 4. So you can shorten it with LC would be equal to 4. Now in some weird cases where sometimes you have functions written like this, like 18 minus t squared, the leading coefficient would be -1. Okay, because this is the term with the highest degree. So if you were writing it in standard form, it would be negative t squared plus 18. So it's when it's written in the standard way, what the first coefficient would be, but really it's the coefficient on the term with the highest degree. Okay, so the absolute maximum is the greatest or least value attained by a function for all values in its domain. For all values in its domain. So this is different than a turning point because it has to be the absolute maximum. So let me try hopefully better to draw these here. It's kind of hard on this pad. Okay, so if we have a curve that looks like this, for instance. Okay, so notice that this is a turning point and it's a local maximum, but it's not the absolute. This is the absolute maximum because it is the highest point that the curve will ever reach. Okay, so here, if we have something that looks like this, okay, then you would have an absolute minimum would be down here. Now, this only occurs if the degree of the function is even. Okay, so that was worth figuring out. Or, I mean, you can think about why it doesn't occur with an odd function. Sorry, not an odd function, a function with odd degree. So something like this doesn't have an absolute maximum or minimum. This is a local max and this is a local min, but this goes up into infinity, this goes down into infinity, so there is no absolute maximum or minimum. Okay, now we get into the end behaviors, and this is a really, really important section, especially when we're getting into graphing. Okay, so the degree determines the type of end behavior. So for example, if the degree of your function is odd, okay, so that doesn't mean that its symmetry is odd. It means the degree of the function is odd. So that's like a linear function, something with x to the power 3 or x to the power 5. All of those have odd degree. Okay, then think about what a line does. So for those with odd degree, think linear. Then they're going to have end behavior that either goes from here up to here or from up to down. So basically, the end behavior is different in either direction. So if it starts from negative infinity, it's going to end at positive infinity. If it starts up here at positive infinity, it's going to go down to negative infinity. So the degree determines the type of end behavior so that it goes from up to down or down to up. But now the leading coefficient will determine the direction of the end behavior. So we're going to go from one to the other. We're going to switch, but how we switch depends on whether the leading coefficient is positive or negative. So just think of a line. If you have something like y equals x, for example, or let's just say x plus 1, the slope here is positive. So you're going to have something, if it was a linear function, that looks like this. Okay, so the end behavior as x goes to infinity, so as x goes this way, y is going to infinity. And as x goes to negative infinity, so we're going in this direction, y is going to negative infinity. Okay, so let me say that again. If the function has an odd degree and the leading coefficient is positive, then this is always true. And the easiest way to remember this is to just think of the slope of a line. If the leading coefficient is positive, it slopes up. So if it's something like a cubic, it would look like this. Okay, so it starts from the bottom and ends at the top. All right, but if the leading coefficient is negative, you guys can guess what's going to happen here. Okay, then think about something like y equals negative x plus 1. Okay, though it's going to slope down. Okay, so as x goes to infinity, y is going to negative infinity. And as x approaches negative infinity, so it goes this direction, then the function is increasing infinity. So if you had a cubic or something like that, it would start from up here, maybe have a couple of humps, and then end up going down. Okay, so before you move on, just take a look at this and make sure you understand the difference. So the degree determines what type of end behavior it is. So it starts in the bottom and goes to the top, or starts in the top and goes to the bottom. And then the leading coefficient, whether it's positive or negative, determines up, down to up, or up to down. Okay? Now, if you have even degree, then you're either ending both up or ending both down. So think about a quadratic. So this would be like x squared, x to the power 4, x to the power 6, anything with an even degree. So think quadratic. Whatever the rule is for quadratics, it's the same rule for the rest. So if the leading coefficient is positive, that's like if you have like y equals x squared, right? Like even x squared minus 4, let's say. That would be something like this. So the a value is positive, so it opens up. Okay, so as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y still approaches infinity. So in either direction, it's going up towards infinity. Now, it doesn't matter if you have like or a cortex, like something that has a degree of 4, even if it has humps in there. If it's of even degree and the leading coefficient is positive, this is what the end behavior will look like. They'll both face up. Now, if you have a leading coefficient is negative, that's something like y equals negative 2x squared or something like that, then it will face down, right? It'll open down. So it looks something like this. Oh. So it faces down. So the end behavior is as x goes to, and you can actually write it this way to save time, as x goes to positive or negative infinity, y approaches negative infinity. So you can either separate out the x's here, like this, or you can write them together because the end behavior is the same in either one. So even if you have some humps going on, if the degree is even and the leading coefficient is negative, the end behavior will end up going down. Okay, now that is really important to understand before you can understand turning points. So if you need a little refresher or need to read that over and pause the video, do that right now, because you need to understand end behavior to understand the rest of this note. Okay, so turning points, this is actually determining the number of turning points. So you might want to add number of. It's not where they are, it's how many turning points there are. So if a polynomial has degree n, it has at most n minus 1 turning points. So think about what that means. That means if the degree is 5, then it has at most 4 turning points. If the degree is 2, it can only have at most 1 turning point. Okay? So, but if n is even, so if that means if it's of even degree, the polynomial must have an odd number of turning points in order to end up going down in the same direction. Okay, so that's what I meant, that you need to understand end behavior to understand these points. Okay, so because if the degree is even, it has to either start from going up and end going up, or start going down and end going down. For that to happen, it has to have an odd number of turning points, because if it had an even number of turning points, it would end up, the end behavior would go down in the opposite direction. So that makes sense that if n is odd, the polynomial must have an even, sorry, it must have none, no, or an even number of turning points in order to end in the opposite direction. So think about it. If this is a polynomial of degree 5, for instance, let's say it goes up and then down and then up. So if I go back up again, if it's an odd function, I can't have my arrow going up here, or else that would mean it was a function of even degree. So it's going to have to turn back down again. And you'll notice there's 1, 2, 3, 4, 4 turning points. So that's an even number of turning points to end going in the opposite direction. So instead of memorizing these points, it's better to just understand the end behavior piece, and then this should come kind of as making sense with the end behavior. Okay, now the number of zeros is also determined by the degree of the function. So if you have a polynomial of degree n, it may have up to n zeros. Okay, so it could have any number of zeros up to and including whatever the degree is. However, a polynomial of odd degree must have at least 1 0. And this is back to the end behavior. If it's an odd end behavior, that means it's going either this way or this way, which means it must cross the x-axis at least once. Okay, but if a polynomial has sorry, let's just say odd degree, a polynomial of even degree may have no zeros. Okay, again, because of the end behavior, because it all goes up like this or all down like this. It may not even cross the x-axis if the x-axis happens all above or all below this situation. So it may not cross. Doesn't necessarily say that it doesn't, but it might not. Whereas if it's an odd degree, it has to cross at least once. Okay, finally, symmetry. Some polynomials with even degree are even. Okay, so like, remember that's when f at x equals f at minus x. But remember, even means that it must be symmetrical on the y-axis, not just with itself. So, for example here, this quadratic is symmetrical, but it's not symmetrical on the y-axis, so it's not even, right? It has to be symmetrical on the y-axis, not just a symmetrical function with itself. So that's really important to remember. And some polynomials of odd degree are odd in terms of their symmetry. Remember, that's f at minus x equals negative f at x. But again, here, it has to be symmetrical on the origin. Okay, so it has to be centered to the origin, or else it's not an odd symmetry. Okay, that's really, again, really important to remember. But most polynomials have no symmetrical properties. Okay, most of them are shifted left or right or up and down, which gets rid of that nice symmetry. Okay, so there we go. That's kind of the overview of these characteristics. We're going to be using our knowledge of these characteristics in graphing, in problem solving. It's super, super important that you have this stuff down and that you're practicing this as much as possible, and that you're able to even understand it to the point where you could explain it to somebody else. So really try, at a minimum, memorize this note, but try to do more than memorize. Try to actually understand why all of this is true. Okay? But here are your success criteria. Can you identify the leading coefficient and the degree of a polynomial given its equation? I mean, that's the starting point. If you can't do that, then none of the rest of this makes sense. Can you identify the possibilities for a leading coefficient and the degree if you're given its graph? So when I give you a graph and you see its end behavior, you should be able to say, hey, that's even, or hey, that's odd. And if, again, you look at the end behavior, you should say, hey, that's a function of even degree that has to have a positive leading coefficient because, et cetera, okay? Can you determine the end behavior if you're given its leading coefficient and degree? So if you're given the equation, can you tell me what the end behavior is? If I give you the degree of a polynomial function, can you tell me all of its possible number of turning points, its possible number of zeros, and the possibility of its symmetry? Okay? And discuss why any of the properties are true. This is key here. Do you understand why they're true? And given information about key features of a polynomial, could you create a possible graph or an equation? So a quick example of this one. If I tell you that the degree of a polynomial is equal to 4, okay, and I say, what are the possible number of turning points? Well, the possible number of turning points we know is n minus 1, so it's equal to 3. But we also know that if a function of even degree must have an odd number of turning points. So the possibilities would be, it could have 1 turning point or 3 turning points. It couldn't have 0 turning points, and it couldn't have 2 turning points. If you don't understand that, make sure you ask me. Okay, the number of zeros, it's an even function, so a function of even degree. So it could have no zeros, or it could have 1, 2, 3, or 4, anything up to and including n. And you determine if this 0 is included or not based on the degree of the function. Okay, and the symmetry, it could be even, but we don't know if it is. All right, that's your note today. Thanks for watching. I hope you learned lots.